Hello, I'm Paul Beckwith. The fundamental question that I want to discuss in this video, and at least the next one, maybe the next few, is why has there been no new record minimum Arctic sea ice extent since September 2012? Okay, there were new records set for September lows in 2003, 2005, 2007, 2012. But since 2012, there have been no new records set. And meanwhile, the global average temperature has been rapidly rising since 2012, obviously. And the Arctic, because of Arctic temperature amplification, the Arctic temperatures have been rising at even much greater rates than the global averages, and yet no new records have been set. So, many people have been wondering, what's going on. And I've suggested that there's a number of possible negative feedbacks that are causing that. And it just so happens that a few days ago, a new paper came out by Jennifer Francis and Bingyi Wu, which asks that very, very question. And that paper relates it to the lack of snow cover both over parts of Asia and the high northern, North America, lack of snow cover in the spring. And so I'm going to, really delve into the details of this question. I won't apologize, but it is going to be quite technical. And, Jennifer Francis, of course, wrote the landmark paper with Francis and Vavris in 2012, 2013, talking about the jet streams, the Arctic amplification, reducing the temperature gradient to the equator, slowing the jet streams, causing extreme weather events, et cetera, et cetera. So it seems that there are some negative feedbacks in play. And, I've often said that because of these slow and wavier jet streams, so they're extending a lot more in the meridional north-south direction. They're slowing down in the zonal direction. They're getting stuck, and that causes an increase in the frequency, severity, and duration of extreme weather events. And it also causes these extreme weather events to occur in regions where they didn't normally occur. I mean, we're talking about torrential rains leading to flooding, widespread flooding in some regions, and heat waves, dryness, drought in other regions. And the reason why this is so important as the Arctic continues to become a darker place with less and less sea ice is that it will distort the jet streams so much. And I've also talked about them being offset over Greenland. So instead of circling the North Pole, they now circle, with no sea ice, they'll circle closer to the center of Greenland, which is at 73 degrees north. So they'll not only become slower and wavier, but they'll become offset. And it's really going to take a toll on our global food supply, and that's how it will affect people the most. But anyway, the waviness of these jet streams is getting worse and worse as the Arctic loses its sea ice and continues to warm. And in a world with no Arctic sea ice, the question is, what will the configuration of these jet streams be? Already we're seeing cases where the ridges of the jet streams carry the heat right up into the North Pole. And this is happening even in the middle of the winter in the North Pole. And we're getting temperatures above zero we have 4 months of darkness up there, but we're getting ridges going right up to the North Pole, bringing hot, warm, humid air. And, in the middle of the winter, so they're extending right up there. And the troughs, meanwhile, are going down as far as the equator. That brings cold, dry air from the Arctic down very, very far south. And these jet streams are actually even crossing the equator, joining with the Southern Hemisphere jet streams, as I've pointed out. Both of these cases, a ridge going up into the Arctic to the North Pole brings hot, humid air up into the North Pole, and that displaces cold Arctic air. So that causes tremendous warming of the Arctic. By the same token, a trough extending all the way down to the equator, going down to very, very low latitudes, is bringing cold, dry air from the Arctic down very, very far south. So that will, of course, cold air will be displaced by warmer air. And again, once again, that causes great warming of the Arctic. So if we look at this Arctic temperature amplification, if you look at the, depends on how you define the Arctic, but the number you've heard quite a bit is that the Arctic is warming twice as fast as the global average. Well, that's not true. It's more like 2 to 3 times, and that's how, if you define the Arctic as north of about 66 degrees latitude, if you can take the 0 degree Celsius isotherm, or the permafrost line, or the tree line, or you can take the Arctic's north of 70 degrees, which a lot of people do, then the Arctic's actually warming 3 to 4 times faster than the global average. If you go north of 75 degrees, it's more like 6 to 8 times faster than the global average. And if you talk about the Arctic north of 85 degrees and higher, it's more like 10 times faster or something than the global average. So it's not just the atmosphere that is changing, that is rapidly warming, but the oceans are rapidly warming. And some of these situations where the Arctic is very warm and the continents are colder, or the Arctic that happens towards the in the spring and early summer. But what we're seeing is so each year since 2012, the melt rates in the Arctic have been extremely high. Well, first of all, the Arctic, the winter amount of ice is less and less and less each year. And then come into the melt in the spring and early summer is extremely fast, and everybody gets excited and says, well, this will be the year there's a blue ocean event. This will be the year there's no Arctic sea ice. And then their thoughts and people are making all kinds of predictions about that, and then those things are shattered because come August, early September, a month to a couple of weeks before the sea ice minimum, the pattern shifts, and basically the Arctic gets a low pressure area over it. So when there's very, very fast ice melt early in this late in the spring and early in the summer, there's a ridge and high pressure over the Arctic. There's not a lot of clouds. The sun is devastating to the ice, but then the pattern shifts and a trough ends up covering the Arctic, and it's colder air, and there's a lot more clouds all of a sudden. So the ice melt rate slows down greatly, and everybody says, well, yeah, maybe next year, right? So this is happening over and over again since 2012. So the question is to try to explain it. Clearly some negative feedbacks are occurring, but which ones are dominating? So I've talked about the ridges going right up to the Arctic and the troughs going really low, and that causes a huge Arctic temperature amplification. Another big factor is the Atlantification process. So the Pacific Ocean off the Bering Strait, and the Atlantic Ocean on the other side through the around the Fram Strait side and the Scandinavia and Russian side, the ocean is much, much warmer, and we're getting marine heat waves. And of course, the density of water is a function of both temperature and salinity. So if the salinity is very high, you can have warmer water of very high salinity that's denser than cold water of low salinity, right? The fresh water from the melt. So that warmer water is underneath, and that water is rising up closer to the surface and melting the ice from below. So this is that's another reason why the ice is being attacked. It's being attacked from the atmospheric temperatures, from the water temperatures below. But then, why haven't we set new records? Well, one thing is that as you get closer to 0 degrees, as you get closer to that temperature, the air can hold very cold Arctic air doesn't hold much moisture. But when you increase the temperature, but you're still, when you increase the temperature, there's more and more vapor being held in the air. You can get more clouds, but also you get more snow. Okay, when you're below zero but closer to zero, so that snow can cover the ice and that insulates it and can prevent the growth. But if the ice is very, very thin and not covered by snow, then it can grow very, very fast because the ice, is a thermal barrier between, say, colder air above and the ocean below. So thin ice can grow much, much faster than thicker ice. Okay, so all of these different factors contribute. So the question is really to tease out the relationships and see, what's really, really happening. So again, the Arctic sea ice decline, it sticks out like a sore thumb, basically, as far as abrupt climate change is concerned. Or it sticks out like, if you don't like the sore thumb analogy, it sticks out like a baboon's bright red rear end, bright red ass, right? I mean, it's totally conspicuous, right? The loss of sea ice is totally conspicuous. The summer minimum is about half of what its extent was 40 years ago. 4 records have been broken in sea ice minimum since 2000. That's 2003, 2005, 2007, and 2012. So the most recent minimum record was in September 2012, and before that it was September 2007. No new records have been broken since then, so why not? And in 2012 we had a massive cyclone go through the Arctic, and that finished off a lot of the ice. It tore it apart and caused very, very rapid melt. So it seems like so what we're seeing, what the data is showing, the observations show, is that the conditions in the Arctic are conducive to very fast, rapid melt in the spring and early summer, and then in August some point, or going into September, there's an abrupt atmospheric shift during in the Arctic, and that's happening during each August or early September. So it brings low sea level pressure to the Arctic. It brings a lot of clouds and unfavorable winds for the ice reduction. Okay, the winds, because it's lower pressure in the Arctic, the higher pressure comes in, deflects to the right, and it stops ice being exported out Fram Strait. But it also tends to, if you look at the vector, the force vector, it tends to spread out the ice. It tends to keep the extent higher than it would otherwise be. So, early in the spring and the summer, there's a ridge condition. It's high pressure over the Arctic. It's clear skies, high pressure, huge ice loss rates. Everybody says, whoa, this could be the year for a blue ocean event. And then come August, early September, the atmospheric conditions abruptly shift in the Arctic. We get low pressure over the Arctic. The ice melt slows, and it doesn't set a new record. Okay, and associated with that period in August or early September, with the low sea level pressure over the Arctic, we get the coldness over the ocean and the warm continents. We get associated with that heat waves, high pressure, and heat waves over East Asia, Scandinavia, northern North America. And the jet stream, we get a splitting of the jet stream. Okay? And the splitting of the jet stream, that actually acts as a waveguide, if you like, and confines the jet stream. And so the jet stream reaches a condition called quasi-resonant amplification, where there's about 6 to 8 waves around the waves around in Rossby waves around the Earth, and that is related to the snow cover in the spring. I'll explain it in the next video. Thank you for listening.